Okay. So there's some concepts from chapter 19 that we use in chapter 20. That's why 20 comes after 19. So we talked about delta G and K, right? Free energy and the equilibrium constant in previous chapters. Now we're talking about standard cell potential. And these three quantities are related to each other. So in a spontaneous redox reaction, we learned for any reaction, if delta G0 is negative, then that will be a spontaneous reaction. We learned even earlier that if the equilibrium constant is greater than 1, that favors the products. And so the reaction will go in the forward direction. And what we just learned was that if the standard cell potential is positive, this will be a spontaneous reaction. So non-spontaneous is the opposite of all of those. So these are related to each other, and we're going to look at how they are related. So potential difference is the potential energy difference per unit charge. And that could also be thought of as the maximum work that can be done. So E, that cell potential, is the potential energy difference in joules divided by the charge in coulombs. So charge is often abbreviated Q, and the potential energy difference being the maximum work that could occur is W max. So then we can say the maximum work done by that system, W max, is equal to negative Q cell potential. So the charge that flows is quantified using Faraday's constant. Faraday's constant tells us how many coulombs are in 1 mole of electrons. So coulomb is a unit of charge. In chemistry, we're dealing with everything in moles, and the unit of charge we use is electrons. So this relates coulombs to moles of electrons. So the total charge, Q, is going to be the number of moles of electrons times the Faraday constant. And this N comes from the moles of electrons in that balanced chemical equation. So we can substitute these things in. We had W max is equal to negative Q standard cell potential. So now we can say that that is equal to NF times the standard cell potential. What we've done in here is for Q, we've substituted NF from the previous slide. Well, the standard free energy, delta G, is the maximum amount of work. So this W max is delta G. So then we get delta G is equal to negative NF standard cell potential. N is the number of moles with electrons, F is the Faraday constant, E0 is the standard cell potential. So that's the relationship between E and delta G. Use tabulated electrode potentials to calculate delta G0 for the reaction. Is the reaction spontaneous? We could also do this by looking at one of the other tables in the appendix that had delta G formation for all these things, but here we don't have that, so we're going to have to do it a different way. So we're going to use that equation. Delta G is equal to negative NF E0 for the cell. And let's remember that F is 96,000, I almost had it, 485. $96,485 coulombs. That's a really bad C. Coulombs per mole. Write those down so we don't have to try to remember them. How do we find the standard cell potential? That's what we need here. We have two half reactions, right? So we find the half reaction and its electrode potential. And then we combine those. The book talks about taking the cathode minus the anode, and that just, it doesn't work for me. So I'm gonna go through this the way it makes sense to me. So what we want to do is this is our balanced, didn't mean to do that. This is our balanced redox reaction. We need to pull it apart and see what are the two half reactions in here. So we only have two reactants, so the sodium must be the reactant for one of them, and the H2O is the reactant in the other one. So the sodium is going to become sodium ions. And then the water is going to become H2 and hydroxide. And when you're splitting this up, just use a little common sense, right? The NAs are going to be in the same half reaction. Do I need any of the other guys for this to be balanced for mass? Do I need oxygens or hydrogens? No, this one's good by itself. So I'm going to put the H2s and the hydroxides with that guy because it must belong over there. Now the one thing we're missing is the electrons. We can do this just by looking at the charges. This side is 0, this side is +2. So this half reaction must be losing 2 electrons. And so if this one's losing electrons, the other one must be gaining electrons. And of course, I forgot to leave enough space for that, so I'll scooch you over. So this one has 2 negative on that side, and so I'm going to need 2 electrons over here. When you're taking apart a balanced redox reaction, the numbers of electrons should match up, because when we add these together, they cancel out, and that's how we get that. So this is half reaction method kind of going backwards. So those are the 2 half reactions. Now we're going to find those in our table. So we've got Na, and this one is losing electrons. These are all gaining electrons. So I can look for this side over here, or I can look for the sodium over there. And we find that right here. Is this reaction written in the same direction as this one? No. So what do I do for E0? I change the sign. So in the table it says negative 2.71. So because I'm doing it backward, this is positive 2.7. That makes sense, right? Then I'm going to find the other one. Oh, what did I do? You see what I did? I was zoomed in too far. I wrote it next to the wrong equation. Now we're going to find this other one. So where'd it go? Looks like it is right there. H2O plus 2 electrons going to hydrogen and hydroxide and negative 0.83. This half reaction is written exactly like this one. It's the same direction. So then E0 is the same. I don't do anything to it. E0 is negative 0.83 volts. E cell is the sum of those. Positive 1.88 volts. You see how I did that? If you can kind of understand the process, then it's not hard to remember. Yeah,
Do the coefficients matter?
great question. Do the coefficients matter? No, they don't in this step. So here we've got two sodiums, two electrons, and here in this one it was all ones, right? We don't need to consider that here. Where this 2 comes in is the n in this equation. So that's the one thing that makes dealing with these guys different than with delta H's. Delta H's, if the equation was multiplied by 2, we multiplied the delta H by 2. We don't do that for E. Okay? Great question. Any other questions? Yeah.
I just have some clarification. I get that for one side of the equation you put the electrons in. That means on the other side. But why for the 2H2O, that's a charge of 0. For the other side, H2OH, that's a charge of -1. So wouldn't you want it to go to 0? Or we put
That's a great question. We do not always have both sides being 0. They need to be equal to each other. Yeah. So there's going to be counter ions in that solution because you can't just have hydroxide ions. There's probably some sodium ions hanging around. Yeah. Great question. So coming up with the standard cell potential is something that we have to do pretty often in this chapter. And so I just want to go over it real quick again with you. You'll most likely be given a balanced redox reaction. And you need to do something using the standard cell potential, and they don't just hand that to you. So you take your redox reaction and you pull it apart into the 2 half reactions. Just keep the coefficients, and what you'll find is that the electrons will be equal in number. 2 electrons lost, 2 electrons gained. It could be a different number, but they'll be the same. And that number is n. So that number is important. That's our n equals 2. So we write out the 2 half reactions. We find them in the table of standard reduction potentials. And then we're going to see, well, is it written in the same direction as it is here? If this one's in the same direction, then you just copy down E0. This one is reversed. So this one's reversed, that means I changed the sign. I'm not going to worry about multiplying by 2. We don't do that in electrochemistry. Then I add these together. Okay, so now we can calculate delta G. Delta G0 equals negative NF E cell. So negative, and N is 2 moles of electrons, and F is 96,485 coulombs per mole of electrons times the standard cell potential plus 1.88 volts. Moles of electrons cancel out. I can do the math here. Negative 2 times 96,485 times 1.88 negative 36278.3.6. And my unit is coulombs times volt. A volt is equal to a joule per coulomb. So if we rewrite that, instead of writing volt, we write joules per coulomb. The coulombs cancel, and there we have our energy unit. The definitions of these sorts of units should be on that table of useful information for exams, because I don't expect you to remember that. I struggle to remember it myself. So, what's a reasonable number of sig figs here? 3, yeah. So, negative 3.63 times 10 to the 1, 2, 3, 4, 5, 10 to the 5th joules. Could also be put into kilojoules. But the answer the book gives is in joules, negative 3.63. Any questions? Yeah. Where do I get the 2 moles? Great question. So N is the number of moles of electrons that are transferred in this reaction. So when I look at these 2 half reactions, I'm going to have electrons on the right and electrons on the left. And the number of them is going to be the same, because that's how you get the balanced redox reaction. So whatever the coefficient is in front of the electron, that's what N is. Yeah.
Is there a time where egg will switch like from a negative to a positive?
No.
It'll always be negative?
Well, there's a negative sign here, but N itself is a positive number.
It's always going to be positive.
Yeah. It's a number of moles. So we can't have like negative 5 pencils, right?
How did you do the conversion?
How did I do the conversion? This part?
Yeah.
Okay, so if we go back to an earlier slide, we talked about a volt is equal to a joule per coulomb. It's way back earlier, the beginning of this chapter. So a volt is a joule per coulomb, so then here instead of volt, I wrote joule per coulomb, and then the coulombs cancel out. Yeah. So a lot of these units are all like related to each other. Like a Newton is a kilogram meters squared per second squared, right? Well, why don't we always use kilograms meters per second squared, right? Well, because it's long and complicated, and if we're just using newtons, force, we just like a single unit. But it is defined in terms of other units. And so most of these units, there's not going to be any coefficients. They're just straight relationships, right? Any other questions? Periodic trends, direction of spontaneity. So here we're given a reaction and we're told it's non-spontaneous. Does the sign of delta G agree with that assessment? For a spontaneous reaction, delta G is negative. This one's positive. So yeah, this is a non-spontaneous reaction. This is not going to proceed in the forward direction. So just thinking about conceptual reasoning, which of the following best explains why I2 does not oxidize Br? And that's a typo. I'm going to fix. That's shouldn't be a D there. That doesn't make any sense. So multiple choice questions, right? Lots of multiple choice questions on an exam. There are strategies for answering multiple choice questions. And using a strategy is not cheating, because you have to have some knowledge to do that. So we look at the three choices here, and we see that the first two are basically opposite of each other. This is bromine's more electronegative than I, so we don't expect Br minus to give up an electron to I2. B is putting iodine and bromine exactly opposite. The last one says, well, bromide is in solution and I2 is a solid, and solids don't gain electrons from substances in solution. Is that true? No, that's not true. If this was true, those electrochemical cells we were drawing pictures of wouldn't work, right? Because we have a metal electrode, and electrons are being transferred between aqueous and solid. So that last statement is just flat out wrong. So then we're picking between the first two. Okay? This one says bromine's more electronegative than I. This one says I is more electronegative than Br. We can answer this question just knowing the trend for electronegativity, which is Chem 1A stuff, right? The way I remember the trend for electronegativity is fluorine is the most electronegative. It has the highest attraction for electrons. So if you're comparing two elements, whichever one is closer to fluorine would be predicted to have the higher electronegativity. Which is closer to fluorine, iodine or bromine? Bromine. So bromine is more electronegative than iodine. So the first part here is correct. The first part here is wrong, so we can eliminate that. Let's just think about the rest of it. So we don't expect Br minus to give an electron to I2. Br minus has a stronger pull for those electrons. Here we've got Br minus, it's got an electron, and it's holding on to it. It really likes that electron. Is it going to hand that over to I? No, it's not. So sometimes there are questions on exams that you're like, wait, we never really talked about anything exactly like that. Well, don't just give up on it. Look at it and see if you can at least figure out part of it, right? And then you have a much better chance of getting the answer correct. Okay, so the relationship between cell potential and equilibrium constant. So we learned that delta G is equal to negative RT, natural log of K. And we just learned that delta G is equal to negative NF E cell. So we can put these two things equal to each other. Right? Just set them equal. And then we can start simplifying a little bit. So the negatives are going to cancel out. So these are both going to be positive. And we're trying to get E cell by itself. So I'm going to divide both sides by NF. So I get E cell is equal to RT over NF times the natural log of K. Three of these letters, two of the letters represent constants. One represents the temperature, and at standard cell potential, we're always talking about 298 Kelvin, room temperature. So we know the value for R, T, and F. We can plug that in here. So R, 8.314 joules per mole Kelvin. T is 298.15 Kelvin. Divided by N, moles of electrons. That's going to be different for different reactions. And then 96,485 coulombs per mole. And so the K's are going to cancel out, these moles are going to cancel out. The unit here we have is joules per coulomb, which is equal to what? Volt. That's equal to a volt. Just another name for it. Don't ask me why, but electrochemists use the base 10 log here. Thermodynamics uses the natural log. So you can convert these. The natural log of something is equal to 2.303 times the base 10 log. So instead of ln k, I'm going to write in 2.303 base 10 log of k. That's just a math thing. I'm not going to make you do this. So if we take these numbers and do the math, 8.314 times 298.15 times 2.303 divided by 96485. So at 25 degrees Celsius, standard temperature, this is the relationship between equilibrium constant and standard cell potential. These equations are all given on your table of useful information for exams. I don't expect you to memorize those. They use tabulated electrode potentials to calculate K for the oxidation of iron by hydrogen ion at 25 degrees Celsius. So we just learned we want to find K. So we need N, and we're going to figure that out by looking at this chemical equation. And we need the standard cell potential, which we're also going to figure out from that chemical equation. So I'm going to take this equation and I'm going to pull it apart into the two half reactions. So I've got 2Fe solid is going to become 2Fe3 plus. And there's got to be electrons in there somewhere, right? So over here I have positive 6 charge, on the left is 0. So that means I must have 6 electrons here. Then the H plus and the H2, that's 6 H plus is forming 3 H2 gas. And for that to be charge balanced, I'm going to have 6 electrons on the left side. So those are my two half reactions. So I need to find them on the table. Well, here, this one's in a box. That's nice. H plus going to H2. H plus going to H2. Do we need to worry that the coefficients are different than the coefficients here? No, we don't. So E0 for that half reaction is 0. That's the standard hydrogen electrode. And then we find the one with Fe and Fe3 plus. And that's here. And that's why we couldn't find it before, is because it's in the bottom half of the table. You got to be careful. We want Fe over here, not Fe2 or something else. And here we need Fe3, not Fe2 or something else. The charges have to be just right. So is this reaction written in the same direction as this one? No, it's backwards. So I change the sign on E. So for this one, E0, the table lists it as negative 0.036 volts. I wrote it backwards, so I changed the sign. I add these together. My standard cell potential then is plus 0.036 volts. So I'm gonna use this equation, oops, I'm gonna use this equation. And so, an exam question, how do I know to use this equation? Well, I've got K and standard electrode potentials, which is E cell 0. Pretty sure this is the only equation on that list that has just the two of those things in it. So usually you can pick the correct equation out of the list fairly easily. Usually don't have to choose too much. So E cell is 0.036 volts, and that's going to equal 0.0592 volts divided by N, and N is 6. 6 electrons lost, 6 electrons gained. You can figure it out from this equation, but it's not as easy. You have to look at the oxidation states to see what's changed. So we're taking these apart anyway so that we can identify the half reactions. This is where we get our number 6. So this is divided by 6. And then we've got the base 10 log of K, which is what we're trying to find. So I can rearrange that and get the log of K is 3.64865. The volts cancel out. And there's a decimal. So to undo the log, it's 10 to the x. So K is equal to 10 to the negative 3.64865, which equals 4453. Sig figs in. What's the unit on the equilibrium constant? There's no unit on the equilibrium constant. If algebra is not your friend, you can also plug this into your solver. Yeah, question?
Oh, that's what I was gonna ask. Does it make a difference, like, if we, like, break it down, or can we just plug in, like, the first equation?
You should be able to plug it into the solver. If you're taking the exam and you're plugging it into the solver and you're having trouble, you can come and ask me for help with your calculator. Okay? Other questions? Yeah.
You said 3.64, 10 to it. Why does it become negative on the exponent?
It doesn't. Thank you. I'm thinking pH. Yeah, there's no negative there. Thank you. There's no negative there. Hydrogen ion is 10 to the negative pH. I think that's where I got that. Thanks for catching that. Any other questions? They give us 4.5 times 10 to the 3. And if we're doing 2 sig figs, this would round to 4.5 times 10 to the 3. Okay, so now we have the relationships. Delta G to standard cell potential is this equation. Delta G to K is this equation. And standard cell potential to K is this equation. Redox reaction has an equilibrium constant of K is equal to 1.2 times 10 to the 3. Which statement is true regarding delta G and delta E? not delta E, E cell for this reaction. So K is a big number. Is the log of a big number positive or negative? I don't know. Well, let's just try a big number, right? So I'm going to take the log of 5,000. Oh, that's a positive number. In our example here, K is a big number, so log of K is positive. This is positive, so E cell has to be positive. So you say, well, E cell is positive. This one says E cell is negative. That can't be right. And that one can't be right. Oh, look, here it is right there. So I don't have to go flipping back and forth. And we've got K being a big number. Natural log of K. I don't remember. Natural log of big number, also positive. If this is positive, R and T are positive, multiplied by a negative, then delta G must be negative. So this must be our answer. Any questions?